What if your robot could choose its own path? In this project, you'll build an Arduino maze robot that senses lines, detects obstacles, controls motors, and improves through testing, just like real autonomous robotic systems. You've already built many of the pieces this robot needs: sensing inputs, driving motors, reacting to distance and lines, connecting devices, and debugging code. Now we bring those skills together through Arduino engineering. The goal is not just movement. It is reliable autonomous behavior. Read the world, make a rule-based decision, act, test, and improve. In this project, your robot needs to handle uncertainty. It senses lines, walls, and intersections, lets the Arduino choose the next move, and relies on calibrated motors to carry it out consistently. Each test run becomes evidence: what worked, what failed, and what to improve next. A maze robot works best when every hardware part has one clear responsibility. The line sensors and distance sensor gather information from the floor and nearby walls. The Arduino acts as the decision maker, reading those signals and choosing what should happen next. Because the Arduino cannot power the motors directly, it sends control signals to the motor driver. The motor driver supplies the needed current and sets motor direction and speed. Finally, the battery pack powers the system. When troubleshooting, follow this chain: sense, decide, drive, power. A robot does not see like we do. It reads clues. Line sensors look downward and measure reflected light. A white surface reflects more light, while a dark line reflects less, so the robot can decide whether the track is under the left, center, or right sensor. Distance sensors look forward. Ultrasonic sensors send a sound pulse, wait for the echo, and estimate how far away an object is. These readings are useful but approximate. Lighting, surface color, angles, and materials can all affect them. That is why we use thresholds, test values, and combine sensor inputs before choosing actions like turn, slow down, or stop. Navigation rules are the robot's decision habits. Each rule connects a sensor condition to an action. If something is too close, turn. If the line is centered, move forward. If an intersection appears, choose a path. The order of those rules matters. Safety rules, like avoiding obstacles, should be checked before normal driving rules. Otherwise, the robot may follow a line straight into trouble. Start with simple if-then rules, test them in the maze or track, then adjust the conditions and priorities until the behavior becomes reliable. Obstacle avoidance starts with one simple question: is the path still safe? The robot reads its distance sensor and compares the measurement to a threshold, such as 30 centimeters. If the distance is greater than that threshold, it keeps moving forward. If the distance drops below the threshold, the behavior changes: stop, reverse a little, then turn. In pseudocode, that becomes: if distance is less than safe distance, stop, back up, turn. Otherwise, move forward. The exact backup time and turn direction depend on the maze. Line following turns sensor readings into simple steering decisions. If the center sensor detects the dark track, the robot is aligned, so it drives forward. If the left sensor detects the track, the robot has drifted right, so it steers left to recover. If the right sensor detects it, the robot steers right. When none of the sensors see the line, the safest response is to slow down, stop, or sweep gently until the track is found again. The logic is simple, but very effective. Intersections are where a rule-based robot stops being only a follower and becomes a decision maker. First, detect the choice. If several line sensors see track at once, you may be at a junction. Then apply a simple rule. The left-hand rule says, if left is available, turn left. Otherwise, go straight or choose the next option. With distance sensors, wall following works in a similar way. Keep one side at a steady distance and correct as you move. Choose the rule that matches your maze and sensors. When both motors receive the same speed number, we expect the robot to move straight. In reality, motors are never perfectly identical. One side may spin faster, a wheel may rub more, the battery may sag, or the robot's weight may lean to one side. Calibration means testing the actual motion, observing the path, and adjusting the left or right speed until movement becomes repeatable. If the robot curves right, the left side is probably overpowering the right, so reduce left speed or increase right speed. Good navigation depends on measured behavior, not just code that looks correct. To calibrate straight movement, treat it like a controlled experiment. Start with a marked lane and run the robot for the same time or distance each trial. Watch which way it drifts. If it curves right, lower the left speed slightly or raise the right speed. If it curves left, do the opposite. Change only 5 to 10 speed units at a time, then retest. Record every setting and result. So improvement is based on evidence, not guessing. Turns need calibration too. Lock in one motor speed first, then change only the turn time. Start with a 90-degree test, run the robot, and compare its final angle to the target. If it turns too far, shorten the time. If it stops early, increase the time. Record the value that lands cleanly at 90 degrees. Then repeat the process for left and right turns separately, because friction and motor differences can make them unequal. Accurate turns keep the robot aligned, prevent wall hits, and protect line tracking. A good robot course should be challenging, but still fair. Start with a simple path, straight driving, one turn, and a clear finish. Once the robot succeeds, add intersections, tighter turns, ramps, or obstacles. Keep the testing conditions consistent, especially the floor surface, lighting, and track markings, so results are comparable. Most importantly, change only one variable at a time. If students add an obstacle and increase speed together, they will not know what caused success or failure. Controlled course design turns each run into useful evidence. Good robot tuning is evidence-based, not guesswork. After each run, record the settings and the results, speed values, sensor thresholds, finish time, collisions, missed turns, and any line loss events. Then change one variable only. If speed, turn time, and distance threshold all change together, you will not know what caused the improvement. Use the data to choose the next adjustment, then test again. Over several runs, patterns become clear. Errors should drop, time should improve, and the robot becomes more reliable through a cycle of test, record, analyze, modify, and retest. You've now connected the core pieces of autonomous navigation. Sensors gather information, rules turn that information into actions, calibration makes movement dependable, and testing shows what to improve. That process is how robots become more reliable. Next, we'll compare Arduino, ESP32, and Raspberry Pi, then move toward camera-based robotics, computer vision, and AI-powered decisions.